Hello, everyone. We have introduced linear regression, multiple linear regression with several x variables. But what we haven't done is we haven't yet found a way of estimating the betas. There are several ways to do so, and we'll introduce the least squares estimate here with a geometric argument. It's a very interesting argument, actually. So the goal is to find a good quality estimate of the betas. We have given a sample of n observations. Each of the observations has a corresponding row here. You see the y's number to n. I added a 1 after the beta 0. It's beta 0 times 1, but just to parallel, it's beta times something. Here I have beta 1 times x11. And they have beta 0 times 1 because it's going to show up on the matrix on the next page. And here are the residuals as usual. Well, we can put this into matrix form. You have a vector of y's. And here I have my x matrix, sometimes called design matrix in experimental design. There's always a column of 1s corresponding to the beta 0. And this order here, the order of the columns corresponds to the order of the betas, of course. Beta 0 is the first column here, so that's the intercept. The order doesn't matter, right? And then I have a vector of epsilons. Now, I can, rather than putting down the individual elements here, I can write this in vector notation. I have a vector of y equals x beta plus a vector of epsilon, a vector of size n. Now, if we look at this x matrix and the vector of the betas, we have n times p plus 1 and p plus 1 times 1. So once you multiply them together, you have a vector of size n times 1. So really what we have is a vector that can be expressed as another vector, x beta is a vector, plus a second vector. So y is the sum of two vectors. Well, this is where geometry starts. We have n observations. And these n observations create an n-dimensional space. Because the observations we observe are random, right? So we're somewhere in this n-dimensional space. Each observation is one of the dimensions. Now, we are expressing this as the sum of two vectors, and the first vector is x beta. X beta creates a p plus 1 dimensional subspace. Now, why would it be p plus 1? Because, well, x is constant, doesn't change, but beta is something we can choose. And there's p plus 1 of those. So we have a p plus 1 dimensional subspace, and that can be expressed here or visually with this oval. If we have only one x variable, and the intercept, then this subspace is just a line. If we have two x variables, then we have a plane. If we have more than two variables, x variables, we have a hyperplane. So, starting from the origin, the 0, 0 spot, we move in this plane. X beta leads to some other point on this hyperplane, whereas the observation y goes into n-dimensional space. So anywhere. Now we know that the first vector has to be in the subspace, but the second vector, the residuals, because it sums to the first vector, has to go from wherever we end up here with the first vector, straight back up to, or down, depending on where it is, to y, right? Because this plus this must be the y vector. The question now arises, where in the subspace do we want to land? In other words, how do we want to choose the betas such that it makes sense in some sense? So we need a criterion here. How should we choose the betas? The criterion that we are choosing is we are choosing to minimize the sums of squares error. Is this a sensible criterion? Well, minimizing the error sounds good, right? That sounds good. Minimizing the sum of the errors also makes sense, right? We have errors from each observation, we sum them all up. And actually, we are summing the squares of those errors. And you can argue whether it's obvious that you want to sum the squares. And it turns out that is a good criterion, but it's not obvious why it has to be the squares. You could conceivably sum up the sum of the absolute values, but absolute values are awkward. And I mean, you could do it. But here we choose the sums of the squares, and that turns out to have some nice properties afterwards. So I'm summing up the residuals here. So y minus the estimate is the residual, so y minus x beta, and but it's the sums of squares. So really what I have is y minus x beta, then I have the Euclidean norm squared, or the residual Euclidean norm squared. Now, what I really have is here, my criterion is I'm trying to minimize the length, the squared length of that vector, of that residual vector. So whether, because it's squared, it's always positive, whether I minimize the squared length or the length of the vector itself doesn't matter. Right? It leads to the same choice of betas. The minimum may be different, but it still leads to the same choice of betas. So what I'm doing is I am minimizing the length of this vector. So how can we place this vector such that it's as short as possible? And the answer is, you're going to try to drop it straight down orthogonally such that you have a right angle onto the subspace here. That is the shortest distance from y orthogonally down, straight down to the subspace. And I have a nicer picture over here. Here is the picture. I'm orthogonal here with respect to all the individual dimensions. And then I'm going straight up. So if I can identify which choice of betas leads me to this point, to the orthogonal point here, then I'm done. All right, so I'm going away from geometry and now going back into equations. The residual vector is orthogonal to the hyperplane. That means that every column of x has to be orthogonal. And so I have here the individual columns. Or I could just write x transpose times the residual equals to 0. Remember that the product being 0 means it's orthogonal, right? So when I take the product and that's equals 0, that's the condition for orthogonality. Now I have my condition and I'm replacing the vector r with y minus x beta hat. And our goal is to find beta here, right? So I've just replaced the residual because I know y equals x beta plus residual, or the other word, residual hat equals y minus x beta. So I have now an expression. I multiply out. I have x transpose y minus x transpose x beta. Put this on the other side, x transpose x beta. And now my goal is to find beta, right? So I solve for beta by pre-multiplying with the inverse of this x transpose x. And then I get beta equals that inverse times x transpose y. That is the solution. Now, this only works when the inverse actually exists here. We will talk about that at some other point, but for now, this is the solution. Okay, so we're really done, right? Because we found the answer. If we like the criterion, least squares, minimizing the sum of squares, then this is the answer. Awesome. So a little afterthought here, even though we are done, because it keeps showing up in books, is the following. We can represent y as the sum of these two vectors, the mean vector x beta plus the residual vector. So mu hat is x times beta hat, where beta hat is our new estimate. And if I plug in this new estimate from the previous page, here it is, and then I make up a new letter for this first part here. So everything that involves the axis is now called H, or the hat matrix. So then I can write mu hat as a function of y, where the function is I'm pre-multiplying a matrix called H. We will not be doing an awful lot with this, but if it shows up, it has some nice properties and it shows up often in books. So I wanted to introduce that thought here when you see it so you know where that's coming from. So I have mu hat equals a function of y, and that function is I'm pre-multiplying the hat matrix. So I can also use that for the residuals. The residuals equals y minus x beta hat. And I'm now substituting the estimate for beta in there. And x times beta hat, both together, just turn out to be the hat matrix times y. Isn't that what we did over here? Yes, x beta hat matrix times y. And then I can factor out the y by adding the identity matrix here. That's the diagonal matrix with ones in the diagonal. And so what we see from this is an expression and there's some interesting properties. But one thing we can get a glimpse at here is that the y's, the residuals here, may not be independent. The estimated residuals are not independent because I am subtracting something of the identity matrix here. So the residuals are independent by assumption, but the estimated residuals are not. This is a glimpse ahead. A little bit too much for now. That was the end for this section.